Okay, let's take a look at using the techniques about frames and machines. We draw the two independent beams and the free body diagrams of those beams. So here we have the force of AB on BC and the force of BC on AB. AB is a two-force member, so that makes it easy. Upward force and sideways force, FAB sine 60. Yeah, 60 degrees, opposite is sine, good. Sometimes I get in a hurry and little things like this, just brush over them too fast and make mistakes. So just be careful about that. You guys will do the same thing. It's something you want to avoid. Okay, now we can look at this beam and we can go through our equilibrium equations. Moment about point A, well, of has to be 0. Let's see. Yeah, this is essentially the condition to be a two-force member. That the let's see. Let's go through this. Being a two-force member, if we have any force, any component of force that is a net force that is perpendicular to the beam, then it'll either translate or rotate. I used the fact that it's a two-force member to write these equations here, and identifying AY to be this and AX to be this, we notice the ratio should be the cosine over the sine. And if you solve this, BX equals AX, by the way, BY equals AY. When you solve this, you see that BX over AX is cosine of 60 over sine 60. So this is essentially proving the fact that two force members are that the forces have to be collinear. Okay, next step. BC. So, and of course they're going to be using this equation, by the way. Okay. And moment about C, 2000, and BY are the only ones that matter. Oops. There we go. Summation of forces in the x direction. That'd be the CX and BX. So they have to be equal. And forces in the y direction, that would be BY plus CY minus 2000 equals 0. So we can go through and solve these. BY has to be 1000. Now, going back here, bx to by, that means you can get bx, which has to be 577. Just like before, cx, and of course cx equals bx, and then cy, combining by here, 1,000 minus 2,000, negative 1,000, which means cy has to be 1,000. Okay. Identify your two force members. Okay, that's part of the point of this. They wanted to show you, it looks like solution one's a lot simpler. Well, duh, you know, rather than going through all this rigmarole. So if you can find two force members, you got something. Now, we want to take a look at this. What analyzing pulleys. By the way, this is an upcoming lab for you guys, is to analyze pulleys. So we have a hook, and we have a joint, a pin joint here. The cable is hooked to the pin joint, goes up over pulley B, around pulley A, up to pulley C, and down to pulley B. So remember, the tension in the same cable is going to be the same. If this is not the same as this, then the pulley will rotate. If this is different than this, then the B pulley will rotate. If this is different than this, then the C pulley will rotate. Here is the total force. It's a different cable, so we can do that. And there will be something pulling on the center of the pulley right here, and the two P forces. Equal and opposite. Here's the two force member. Equal and opposite, that's T. And two forces acting down. This is on pulley B, and then pulley A. So pulley B, right over here, pulley C. What I just circled is becomes the free body diagram for pulley C, pulley A, free body diagram. P and P, tension in the cords. P, tension in the cords, 600 newtons. So we can see that P has to equal 200 newtons instantly. T is 400 newtons. And here we have 400 and two 200s. That's 800. So R has to equal 800 newtons. Okay. So the book talks about, you know, all the different things. P is 200, T is 400, R is 800, just like we came up with. Okay, now little trickier. Two force member makes it easier. So we have 800 newtons. This is, you'll notice this is 30. So we have 30 degrees here from the horizontal. That would make this angle 60 degrees. Oops. Getting the geometry right is a little bit trickier on this problem. So this is 60 degrees, 30 degrees, 30 degrees. So that you're convinced that this is 30 degrees from that this is 30 degrees from the vertical, 800 newtons. It's 90 degrees from the beam itself. Two-force member, FAB, FAB. You've identified the two-force member. Here we have the pin D. Here we have P. Here we can get DX. And we can get normal force. So it's a pin, it's a machine that's designed to crush cans. And this is the configuration of it. This is a cutaway view, by the way, which means there's probably a slot here to allow free movement of this pin in this direction. Let's see, what else? Oh yeah, FAB, we got to be careful about that. So we're getting all the angles of the forces compared to this EBD beam. Okay. Yeah. So looking at this beam, so they really don't go into solving it. Let's go ahead and solve it. But we'll pick it up on the next video.